By the age of 4, most children know how to count to 10. It's some of the first math we're exposed to. One lake, 2 buoys, many trees. As we grow older, we are able to count higher and higher. But where does it end? What numbers can be counted at all? Today, we're going to attempt counting some different sizes of infinity. It would take an awfully long time to count to infinity in the normal sense. So we'll have to think of a different way to count. Take a look at these 2 piles of rocks. Normally, if we wanted to know which pile had more rocks in it, we would count both of them. But is there another way? Let's try pairing them off. 1 rock with 1 rock, until one of the piles is empty. We know that that pile was the smaller one. And if neither pile runs out before the other, we know that they must have started out as the same size. The advantage of this sort of counting by comparison is that there's no limit on the size of the piles we can count. We just pair them off until one is empty, or they both are. Let's put this method to the test by comparing 2 infinite sets, the positive and negative integers. I've only put a few rocks here to illustrate, but the negative integers start at -1, then go -2, -3, -4, all the way down, and the positive integers start at 1, 2, 3, and go up. Intuitively, they should be the same size. We can pair these rocks off like so. The 1 rock goes with -1, 2 goes with -2, 3 goes with -3, so on and so forth. We can see that neither pile will run out before the other one. No matter which positive number you think of, say 142, there will always be a negative to go with it, like -142. What if we compare 2 other infinite groups of rocks, like the positive numbers with the multiples of 2? Intuitively, it seems like we should have more positive numbers than multiples of 2. After all, each multiple of 2 is a positive itself. However, we can pair these rocks up in a cleverer way to show that the piles really are the same size. 1 goes with 2, 2 goes with 4, 3 goes with 6, so on and so forth. Again, neither pile will run out before the other, and any number has a multiple of 2 to pair with it, like 142 to 284. Crazy as it sounds, this shows that there really are the same number of positive integers as there are positive multiples of 2. And as it turns out, we can also pair up the positive numbers with the integers, so positive and negative, or even the fractions. They're all the same size of infinity. But don't be fooled. There really is a simple set of numbers that is bigger than the fractions, bigger than the integers, bigger than the naturals. This is where Cantor's proof comes in. Cantor's argument shows us that there are actually more decimals between 0 and 1 than there are natural numbers on the number line. The argument goes like this. Suppose we have found a way to pair up all the natural numbers and the decimals between 0 and 1. No matter what, at the end of the day, there will still be decimals that aren't paired up with natural numbers. How do we know? Where is this missing decimal? Well, as the argument goes, we can look down the diagonal row of this table to find it. As we go down the diagonal line in this table, let's copy each number we hit to the bottom, and then add 1 to it. So the 0 turns into a 1, the 5 turns into a 6, the 3 turns into a 4, and so on. After we're done with this process, we will have found an entirely new decimal number that we did not account for before. After all, this new decimal can't be the same as the first decimal in our table because it has a different first digit. It can't be the same as the second decimal in our table because it has a different second digit. It can't be the same as the third decimal in our table either because it has a different third digit. This new decimal we've just found was not accounted for when we made our list, and it means we weren't able to pair off all the positive numbers. So no matter how clever we were when we made this original list, there's always going to be a decimal we forgot about. It's crazy to think, but some infinities, even if they don't look like it, really are bigger than others. Thanks, Cantor.